And thanks to the library for putting this on also. Appreciate that. And yeah, in this lecture, I'm going to talk about stars, how they work and all that, and the sizes of some of the stars, and how small they get, how large they get, and the amount of stars and all that. And so might as well shut the lights off, and then we'll begin. Let me just make sure I can see the arrow here. Okay. So this is a picture of our galaxy. This thing would actually wrap around us, but it's like taking a globe and putting it on a flat surface. And over here in our summer sky, we have in the south when the sun sets, we're seeing about from here up, and maybe to about here, I guess, would be our summer sky. And we have the teapot of Sagittarius in the center of the galaxy. Is if you find the teapot where the Polar star is, maybe about the center of the galaxy is right about there. And then here, right here, we have the Alpha Centauri system. This one star is actually three stars, the closest star system to us. Basically, this is the Milky Way band, and these are all gases and dust, nebulas that sit between us and the faraway stars that sit behind this. And those nebulas in the future, a lot of those will collapse to form new generations of stars. I'm just having trouble seeing the arrow here. There we go. Now, if we could be out of our galaxy and look at our galaxy on a side view, it would look like this, basically a flat disk. Our galaxy is about 1,000 light years thick and about 100,000 light years in diameter. Massive galaxy, even though there are larger galaxies. And let me see, yeah. In fact, over here you have two satellite galaxies, the large and the small Magellanic clouds. And those are galaxies that are gravitationally bound to our galaxy. Oops, let me see here. Oh, there we go. Okay, wrong. And our galaxy, they think it's got a wobble in it, probably caused by the large Magellanic clouds as it went by. This is just a graphic, not a photograph, obviously, but that's what they think our galaxy has a bow in it. And if we can see above our galaxy, this is what we see. We're located right about here, about 26,000 light years from the center of the galaxy, and about the same distance to the edge. And you see all the constellations that are around us. And we consider our galaxy a bar spiral. Well, basically this bar of stars, and it's basically a two spiral arm galaxy. We used to think ours was a four spiral arm. We have these stragglers here. But basically a two spiral arm galaxy, basically 100,000 light years in diameter, 1,000 light years thick, and roughly between 300 and 400 billion stars in our galaxy, and enough gases and dust, the nebulas, to form about 3 trillion new stars in the future. And this is a real galaxy, very similar to our galaxy. Again, a barred spiral. And let me get rid of my glasses here. I think I'm missing the arrow here. There we go. Okay. Yeah, in our galaxy, the stars, like 3 to 400 billion stars, a number it's even hard to comprehend. And more stars here. And each one of those stars its own sun. And then we get into the universe. There's the Hubble Deep Field, and I don't know if there's any stars. I guess there's one star right here, another star. But every other dot there is a galaxy. These closest galaxies are probably 9 billion light years away. And you get these red little dots. They're close to 13 billion light years away from us. And it basically what we're seeing these galaxies as they looked in the past. As light has to travel to us, it's taken these galaxies light billions of years to reach the Earth. Oh, wrong button again. There we go. And more galaxies there, and some more galaxies here. Like the estimate now in the visible universe, they're estimating about 2 trillion galaxies in our universe. But that's only what we could see. The farthest stars, there's probably more galaxies beyond those, but that light has just to reach us. And so in the visible universe, there are about 2 trillion galaxies. Wrong one again. And here's some nebulas, and stars are formed in nebulae, these clouds of atoms. All these stars here, they're all new stars under 1 million years old, and all formed from this nebula. And you probably remember this one, the pillars of creation. And just show you how long this is. This right here, that's about 4 light years long, about the distance from us to our closest star. And a big star-forming cloud. And this is just a small cloud in a larger cloud. And you can see the pillars right here. There's the Eagle Nebula, which is up right now. And hundreds to thousands of stars can be created at the same time in these nebulas. Oop, wrong one again. And
Excuse me, Rick?
Yep.
Are these pictures from the Hubble, or where are they taken?
Yeah, some of them from the Hubble, some I have from the Webb telescopes, and some from other telescopes. Yep. And then we have the Orion Nebula, which is up in the winter sky. And inside this nebula here, there's thousands of new stars being formed. And around some of the stars in there, we can actually see planets being formed, new solar systems being formed. And now we get to the stars. And these are the stars, they go from M, from the smallest red dwarf stars, all the way up to O, the largest stars. And these stars here, well, I'll start with the M stars. The M stars can be as low as 8% of the sun's mass. Very small stars. And then you get up the sun is considered a G star from its mass, and the F a little bit bigger, and you get up to the O's. And these O stars can be 50 times the mass of the sun. And you get down to these, the B stars would be tens of times the mass of the sun. So very massive stars, and this is basically the size of they'll be during as they're fusing hydrogen to helium. And most stars, or all stars when they begin, well, I should say all stars are mostly hydrogen. And in hydrogen, if you get to the center of these stars, the pressure is so great and the temperature, and atoms are moving around. But normally atoms, because they have the same electrical charge, when they get close together, they'll repel. But when they get in the middle of the star, like the middle of the core of the sun is about 26 million degrees right now. And once the temperature reaches about 15 to 16 million degrees, the atoms are moving so fast that they actually slam into each other, and they don't repel, and they stick together. And you have one proton hydrogen will combine with 2 protons to make a helium atom. The number of protons determines what kind of element is. Hydrogen has 1 proton, helium 2, lithium 3, carbon has 6, and then uranium has the most, for the natural elements, it has 92 protons. But inside the star, they're moving so fast, they slam in together, and the protons start sticking to each other, and when they stick together, they make different elements. Did you have a question back there, or were you just raising? Oh, just stretching? Yeah.
So all these stars, I guess, depending on time or whatever, heat, have different elements in them. Well, like you said, helium or uranium or whatever, because there's more collisions going on, or more protons, I mean.
Yeah. Inside the star, depending on the mass. Like the sun is hot enough right now, it's fusing hydrogen into helium, and then you're going to end up with a core full of helium. And then those 2 proton helium are going to fuse 3 of them together to make a 6-proton carbon, and 2 more are going to combine to make oxygen. So basically, after the sun fuses the hydrogen into helium, it's going to fuse the helium into carbon and oxygen, and that's as far as it goes. The more massive stars, they have more heat, and they can then fuse the carbon and oxygen into all the elements up to iron with 26 protons, and that's as far as you get as far as the core goes with the fusion. And these are some of the stars, how they qualify the stars. The main sequence, whenever you hear stars in main sequence, that to me is fusing hydrogen into helium, and all stars start that way. But they label the stars on the temperature and the mass. And this should actually be on this side, but you have the smaller stars here. Then you have the red giants over here, which will be like maybe the K stars, but usually the G stars up will turn into the red giants, and that's when they start fusing the helium and the carbon. And the added temperature will expand the sun out into the red giant. And then you have the super giants, which are just massive stars, but we'll get to that. And there's another thing with some of the stars. You have the smallest stars down here, the red dwarfs, and get up here the K, the G stars like the sun, and you get up there to the O stars. And then these up here are the sizes of once they start fusing. They get past fusing hydrogen to helium, and they start fusing the helium, and that expands the stars into the red giant as they get more heat. And here's the smallest stars, the red dwarfs. And right now, this is the smallest star that we found. It's about 8% the diameter of the Earth, about 8% of the mass of the Earth, about as small as a star can get, and to be fusing the hydrogen into helium. Then we have, of course, compared to this planet Jupiter. And then you have Proxima Centauri, the closest star to us, which is a red giant. And that's about 12% of the sun's mass. And here's a picture of Proxima Centauri, the closest star to us. And then you have the Alpha Centauri system. It's 3 stars. And the brighter light looks like 1 star, but it's actually 2 stars that are pretty close to each other, both just slightly larger, more massive than the sun, but very much sun-like stars. And then you have the...
Question.
Yeah.
Do the different types of stars, as far as the size and the type go, do they tend to form in certain regions of the galaxy, like closer to the center or closer to the arms?
No, the mass of the sun really determines how much gases and dust are in the nebula that's forming. You know, most stars, like for every 10 stars you see in our sky, there's there's 7 times more red dwarfs than the larger stars. It's a lot easier to make a smaller star than a massive star. You know, maybe 1% of the stars in the universe are the O stars, the really massive ones, because it takes so much mass to make those stars. But you know, in these nebulas, you can get hundreds of thousands of stars forming at the same time, and their mass depends on how much gases and dust they're collecting.
And are the nebulas that are there, are they from exploded stars, or are they original universe material?
Yeah. Well, when the universe began, like within 3 minutes, the temperature. Well, when the Big Bang happened, the temperature was a 1 with 32 zeros, whatever temperature that is, trillions and trillions and trillions of degrees. And as soon as the Big Bang happened, that trillions of degrees temperature dropped in 1 second to 10 billion degrees. After 3 seconds, dropped to 1 billion degrees. And at that temperature, the energy actually, that quick drop in temperature of the energy actually made the energy basically freeze into the points. And these points are called quarks. And when you take a proton and a neutron, they're made of there's 6 types of quarks, but if you take they all decay really quickly into 2 of them called up and down quarks. And so in the first few seconds of the universe, the temperature was up here, just dropped, and those particles froze into quarks. And then the up and down quarks, when you take 2 up quarks and 1 down quark, you form a proton. And if you take two down quarks and 1 up, you form a neutron. And within 3 minutes after the Big Bang, all the protons and all in the universe were formed. And 1 proton is 75% of the matter was 1 proton hydrogen, and some of that fused together to make 2 proton helium. There's just a small smither of lithium and beryllium with 3 protons and 4 protons. But basically, the whole universe is mostly hydrogen, which collected in galaxies, and then the clouds started collapsing into stars. And so basically, the whole universe of stars start off basically mainly as hydrogen. And then in the fusion process, that's where the heavier elements come. They're basically cooked inside of stars, which we'll get to. Yeah, that's all right.
You just mentioned earlier
that
we can see back. I mean, the Big Bang is what, 13 billion years ago?
13.8.
Okay, and you said we can see. I thought you mentioned some stars or galaxies were 13
Yeah.
Like, so we can see back now as far as the Big Bang?
Yeah, if you take the James Webb Telescope, which you can see the farthest stars, they're seeing stars that were basically, I think, like 400 million years after the Big Bang they were formed, which is a lot earlier than they thought they were formed a couple years ago. They thought it took, a billion years for stars to form, but now they're finding that the galaxies and stars formed a lot quicker than we thought.
One thing, you said something about freezing. So before the Big Bang, it was hot out there, or just that?
No, I'm saying when the Big Bang happened, the temperature of the universe was smaller than, thousands of times smaller than an atom. And inside that was all the energy of the universe packed in there. It was, a trillion degrees, maybe not that much. Yeah, and one with 32 zeros, whatever temperature that is. And when the Big Bang happened, it went like this, and as soon as it expanded, the temperatures dropped. After 1 second, it dropped to 10 billion degrees, and after 3 seconds, it dropped to a billion. And at that temperature drop, the energy actually, they call it frozen, but it's basically just, they basically froze into particles of just points of energy, and that's what a quark is. And then when you combine quarks, you make protons and neutrons, and those are all formed in the first 3 minutes.
Do they have any idea, or they have any speculation about how big the non-visible universe is, or is there no way to tell, or do they have some calculations that estimate that?
They think the smallest the universe is like 1,700 times larger than what we can see. But it could be a lot more than that. They're not sure. They're saying it's at least that. Yep. And it could, and yeah, well, I'll just end it with there, I guess. And so here we get to the red dwarfs, the smallest stars, and these stars are amazing. Even a red dwarf that was formed 13.5 billion years ago, it's still in its infancy. These stars will last trillions of years compared to the sun, which will last about 10 billion. And the reason for that is you have the core here fusing. These are very small stars and cooler stars than our star, so they fuse slower. But they have convection right to the surface. And so, like our star and most stars, they only fuse what's inside the core. The outer layers basically doesn't make it into the core. But these stars, they fuse basically all the hydrogen in the star, with the convection. Convection is like boiling water. You heat something up, it rises, it cools, and it sinks. It's basically a convection of heat. And so you have a lot, red dwarfs basically fuse all the hydrogen within the star. And they can last up to 4 or 5 trillion years of these stars, the smallest stars. And then eventually, it's going to, when the trillions of years, we've never seen one of these. It's called a blue dwarf. But after trillions of years, after these red dwarfs finally use up the hydrogen within them, gravity will crush them, build up the temperature, and they turn into blue dwarfs, which are even smaller stars, but they'll start fusing the hydrogen into carbon and oxygen, and then they're going to die after that. And they just become a white dwarf after that. And a white dwarf is basically a star, is basically a ball of carbon and oxygen and electrons, a little bit bigger than the Earth. And most stars, or just about all stars, up to about just under 8 times the mass of the sun. 8 times the mass of the sun. They'll end their lives as a white dwarf, basically a ball of carbon and oxygen. And so here we go to our sun here. We have our sun, Sol, is its name. A little less than 1 million miles across, 864,000 miles in diameter. It contains about 99% of all the matter in our universe. And the sun is fusing at the core. It's fusing 600 million tons of hydrogen every second into two proton helium atoms. And in the process of doing that, it loses a gamma ray, and that's our light. And in every second of the 600 million tons of hydrogen, 4.26 million tons is turned to energy. And we see that eventually as light. And now, if you're out in the sun, they say, everybody thinks our sun's a yellow star, but if you're out in space, our star is actually a white star. Even it's called a yellow G star, but it is a white star if you were out in space. And in our sun is basically a giant ball of plasma. Plasma means normal atoms. They have the electrons orbiting the nucleus. Plasma just means that it's hot enough that the electrons are free. When it gets, I forget the exact temperature, millions of degrees, it'll fling the electrons off the nucleuses, and the nucleus is just flying around free, and that's what a plasma is. And basically a giant plasma, and you see all these magnetic loops here, and that's from there's so many magnetic lines because it's just a rotating ball of gas. There's another shot of it here. And basically just pieces of the sun, protons and neutrons, they just follow the electrical lines where you get these loops here. And then these loops, they always have a north and a south side, and these things are waving around, and they get a positive and negative side, I should say. And when they hit each other, that's what causes a solar flare. And there's a solar flare there. And these things are whipping, and they shoot off, and these things will come flying at us a million miles an hour. And it's basically just pieces of the sun, protons, neutrons, and electrons, charged particles. And we don't want one of those hitting the Earth. I mean, they hit them all the time, but sometimes the massive ones can cause a lot of damage to our electronics. Oop. There we go. Okay, and now our sun, what's going on? We have the core here, about 26 million degrees. Then the radioactive zone, the convection zone, against it like boiling water, and the light is formed here. Let me see if this next. Yeah, I'll go here and then we'll jump back. This is basically what's happening with the fusion within the sun. And both of these are the same. I'll start on this side. You start out with two protons, the red, and it joins, when they combine, they release a gamma ray and a neutrino. I'm sorry, not a gamma ray, a positron, which is the antiparticle of electron. And they release a neutrino. Neutrinos are almost massive particles, and each second there's hundreds of billions going right through us and right through the Earth without they don't even know the Earth's there or us. They go right through everything, and you come here and then you end up with a proton and a neutron, and you have another proton which joins it. And when it joins it, when it fuses, it releases a gamma ray, which is light, which is the sunlight that we see. And it forms a two-proton a helium atom, but with only one neutron. And then you get the other side to combine, and it shoots two of the protons out, and you end up with a helium atom, two protons and two neutrons. And so that's what's going at our sun at 600 million tons per second. Yep.
This fusion, they talk about helium atoms,
yep.
But these are atoms not as we think of them. They don't have electrons orbiting them at that point.
No, yeah.
They're just
basically just the nucleus. Yep. Yeah, basically just the nucleus. Yep. Yep. Inside the sun or stars, yeah. And so when the gamma ray is formed in the core from the fusion, the light we see is actually up to 500,000 years old. Once the photon hits the surface, it takes about 8 minutes and 20 seconds to leave the sun and reach us. But when it's formed in here, to get out of the core and get out of the radioactive zone, which is just packed with protons and neutrons, basically the photon moves a little bit. It basically does a zigzag. It runs into an electron or a proton, and it could shoot out in any direction after it does that, so it couldn't come up here. It basically does this pinball shot for 500,000 years. It'll be going up and down, and hitting it all, and eventually it'll hit the convection zone. It takes about a month to leave the convection zone to finally leave the Earth. So the light that we see from the sun could be like 500,000 years old, some of it. Pretty amazing. When you think about that. And so that's what's going on in our sun. And our sun, again, almost 1 million miles across, 864,000 miles in diameter. And so that's how our sun's working. And this is what our sun, the life of our sun. Today we're up here. It's the size it is. In about 7.5 billion years, the sun's going to start. The core is going to turn to hydrogen, and it's going to start fusing the hydrogen to helium. And you have the core here, and then around the core, you're going to have a shell of hydrogen that's going to start fusing the hydrogen to helium. But inside the core, it's going to start fusing the hydrogen. It's going to start fusing the helium into carbon and oxygen. And the core is going to crush itself before it does it. And it's going to build a temperature up to about 100 million degrees, and then start fusing the helium into carbon and oxygen. And that added temperature is going to expand the sun into a red giant. And it'll do that for a few more million years, and eventually, it may or may not swallow the Earth. Venus and Mercury are pretty much going to be inside the Earth at that time, and eventually the outer layer is going to blow off the sun, and you end up with a nebula like this, the Eskimo Nebula. Inside there, that's not the star, but it's even smaller than that. It's basically losing its outer layers, and that's what's going to happen to our sun in 7 to 10 billion years. And we have another one up here.
But before that, it'll destroy the Earth about half of that time before that, right?
Well, the Earth would be a livable planet for maybe another billion years, because the sun's going to it's getting hotter and hotter, and maybe about 700 million years from now, you wouldn't want to be standing on the Earth. It's going to be hot. And within a billion years, it's basically going to boil the oceans and the atmosphere away to space. So the Earth would be a livable planet for about 1 billion more years, roughly. Yep. And another nebula here, the outer layers of a star. And the same thing with this, the Ring Nebula, which is up right now. The outer layers of a once sun-like star. And eventually, the core of the sun will be again a white dwarf, a big ball of carbon and oxygen. And here's a white dwarf right there. That's the star Sirius, which is out in the southern sky right now, southeastern sky, when the sun sets. But a white dwarf orbiting the Sirius, our brightest star in the sky, and it's 8.6 light years away from us. Now here we get to the biggest stars. You see over here, we have our sun over here, they have Sirius over here, and now Sirius and this thing is just a little dot here, and you get to the bigger stars, Arcturus, Aldebaran, and then if you put Aldebaran over here where it's just a dot, you get to the real biggest stars, and Betelgeuse, Antares, and then the largest star here, VY Canis Majoris is actually its name. Just massive stars. It's over 2 billion miles in diameter, the largest star. And 3 stars that are up in the winter sky are the Orion Belt here. Right here, that's where the Orion Nebula is, if you have a pair of binoculars in the wintertime or a telescope. But these 3 stars are massive stars. You have here Alnitak, about 24 times the mass of the sun. And you have Mintaka here is about 20 times the mass of the sun, and in the middle here we have Alnitak, and that's about anywhere between 40 to 64 times the size of the mass. 40 to 64 times the mass of the sun, I should say. All 3 of those are massive stars. And up here you have Betelgeuse up here, and down here you have Rigel, which is another massive star. And Betelgeuse, we're actually waiting to go supernova. It could happen. It might have happened 500 years ago. It's like a little over 500 light years away from us, or it might not happen for another 10,000 years. They're not really sure. A couple of years ago, it dimmed out a lot, and they thought it might be going supernova, but it turned out there's a cloud of gas between us that was making it dim. And so here we got the more massive stars, and these stars would be over 8 or more times the mass of the sun. And they start off basically burning hydrogen to helium, and then you start getting, at the end of the life, they start building, every time the core turns to a new element, once the core turns to helium, the gravity's going to crush that core, build the temperature up, and then it'll start fusing the carbon, and once the core turns to carbon, it'll start crushing that core, which will build the temperature up even higher. And then towards the end of the life, the core will be over 1 billion degrees. And at that, the largest stars at the end of their lives, they turn into like onions, where you get all these different elements fusing. And then eventually, the core is going to turn to iron. Well, first it'll turn to silicon before iron. And then within 1 day after the core turns to silicon, in about 24 hours, that extra heat is just going to really quickly turn all that silicon into iron. You end up with an iron core, and the fusion stops here because you need trillions of degrees to fuse iron. And so what's going to happen with a star, there's two things going on with a star. The gravity wants to crush the star, and at the same time the heat being generated at the core is pushing the star outward. But once the core turns to iron, the fusion is going to stop, and the temperature is going to grow less and less and less, and eventually it's going to reach a point where the gravity pulling in is stronger than the pushing out. And when that happens, in less than a second, this whole core just collapses down to about 11 miles in diameter. And at the same as that crushes, as that starts contracting really quickly, the outer layers come rushing in, and then the core builds up this temperature, and it starts forming all these neutrinos. And it's got more energy than the star will have in its entire lifetime. And all of a sudden, those neutrinos just come flying out. And basically, as the inner core is coming in, these neutrinos fly out. And it kind of does this. It presents a shock wave into the trillions of degrees. And that'll fuse all these other elements in the outer layers up to all the elements up to uranium with 92 protons. And every element that makes everything. And that's where we come from, and all the planets and all the stars, or not stars, but anything that's made from anything higher than hydrogen. So, basically, when you think about it, all the atoms that make us, the iron in our blood, the calcium in our bones, the phosphorus, and everything is made inside of a star that blew itself up, as well as the Earth, all the iron and all that, and silicon in our rocks and on the planet. So that was all made inside of a star that blew up. So without the supernovas in these giant stars, we have nothing but hydrogen and helium in the whole universe. But luckily, these stars blow themselves up and fuse atoms, and they make us and give us life, I guess you could say. These are just a couple quick pictures of Betelgeuse. Oops, let me go back here. And Betelgeuse is a really cool star. It's not really round. It's so hot that it's basically bulging out. It's just basically, the convection is like really huge in it, and it basically heats up, and it just sends these huge bubbles, and you can see here, just one side will come out, and so it's basically a star. It's not round. It's basically just fluctuating in and out from the heat from the interior. And here we look towards the center of the galaxy. And just give me 1 second here. Oops. And here we look at this is our summer sky right now. In the south, we have Scorpius here, then Sagittarius, and again the center of the galaxy is right about there. But another star that's going to blow itself up at any time is this star here, Antares, which is a red star. If you look towards the south, it's a fairly bright star in Scorpio. And just like Betelgeuse, it's also going to go supernova at any time. And Betelgeuse has a diameter of about 600 million miles, and this star has a diameter of about 800 million miles. Both massive stars there. Now here we get to the biggest star compared to our sun, VY Canis Major here. Just give me 1 second, kind of talking. Let's find my notes on this one.
And where is that star located?
This one is in Canis Major, which is up right now, actually. Yeah, this star here is 2,453,760,000 miles in diameter. A massive star. And it's got 17, the mass is about 17 of our suns, about 17 times the mass of the sun. It's a red hypergiant, as you can see. And it's about a little over 3,800 light years away from us.
Is that in our galaxy?
Yep.
It is.
Yep. Yep. Yeah, you can't see it with your eyes. Probably with a pair of binoculars you can see it. A telescope you can definitely see it. But yeah, it's up in our sky. Yep. And this is the largest star they found so far. And I mean, the sun is just a tiny blip next to it. Yep.
Is it that large because it's a red giant expanding?
Yeah. Yeah.
So it's at that stage of its
Yeah.
life where it's kind of pushing out.
Yeah. Yeah. Most stars, once they get away from the hydrogen, they start fusing the helium. That extra temperature will expand them out to a red giant. Yep.
Quick question. How large usually are supernovas for stars of that size?
How large is a supernova?
Yeah. Does supernova size depend on star size/mass?
Well, the mass determines whether it'll have a supernova or not. Most stars, 8 times the mass of the sun or over, will have supernova. Will end their lives in a supernova if you're 8 times or more times the mass of the sun. Yep. Anything under that will end up as a white dwarf. Yep.
And a supernova is the death of a star.
Yeah. Yeah. Annihilation of the star. Yep.
When that supernova happens, are all of the elements, have been when it explodes, or have all those elements been transformed into those heavy elements, or is there a mix of hydrogen and silicon and carbon? Do you know what I mean? Like,
yeah.
So is the dust that forms after that, is it just heavy elements, or is it a mix of all?
It's a mix from anything from helium with 2 protons up to 92 protons.
And is the dust, when you say dust, is it molecular sized dust? Or
Yeah.
Are they little particles, or are they clumps of rocks?
Yeah, basically you're just the nucleuses of the atoms. But some of them join together to form molecules, though. So there's atoms and molecules. Molecules are just when more than one atom sticks together. Yeah. Oh, wrong button again. Yep, and here's a couple supernovas. This is a Crab Nebula. This one was visible from the Earth in 1034, in the year 1034, I believe. And and so within this, you have all the elements to make everything. And then inside the center of this is the remaining core, which is a neutron star. Am I hitting the right one here? No, I'm not. A couple other supernovas here. Another one there, just the remnants of the star. And then what's left is this core, is a neutron star. And so you basically have the core, and when gravity crushes the core, you have the atoms which are made of electrons, protons, and neutrons, even though the electrons are free because of the temperature being a plasma. And when it crushes, the electrons are actually pushed into the protons, giving them a little added weight, and it turns them into neutrons. And it basically crushes it down to about 11 miles in diameter. You end up with a neutron star. And the neutron star, it's so dense, a teaspoon would weigh, I think, 5.5 tons, just for a teaspoon. And if you could if you could stand on a chair, 3 feet off the neutron star and then jump off, and that 3 feet, you're going to gain about 500 miles an hour and slam right into that. The gravity's so strong. So don't do that. But just to show you how strong the gravity is there.
So anything going in anywhere near it would get sucked in.
Yeah, well, sucked in, the gravity's going to pull you in. Yeah.
Pull you.
Yeah. As some neutron stars are pulsars where they're spinning. They, even though they're 11 miles in diameter, some of them can spin 700 or 800 times per second. And when it does that, you get this almost like a lighthouse coming at you with the light coming off it. Yep.
Some neutron stars actually have a back of quarks for their core.
I'm sorry, I didn't hear you.
Some neutron stars
Um, I, I, well, the quarks are going to make the protons and neutrons, or So, but basically, it's going to be. I think I was reading there's some debate on that whether the neutrons actually break apart inside, so maybe you could have free quarks. I'm not sure if that's a thing, but.
Sometimes the pressure is so immense that
Go up, buddy. Go up, go up, go.
sometimes the pressure is so immense
The spider.
that quarks can
I got 'em.
actually dissolve from their neutrons and protons and just be stuck in a high pressure chamber.
I don't know about that, but I take your word on that. But I know I was reading that they think that they're insinuating maybe that some of the quarks do, some of the protons, or some of the neutrons inside do break apart into the quarks that make them. Hello, you can come in and watch the end if you want. And then, so for stars, 8 to 23% times the mass of the sun, those are going to always, or usually, they're going to collapse into a neutron star. If a star, if the core ends up with a mass of 24 times the mass of the sun or larger, those stars are going to collapse into a black hole. And this is a black hole, there's a picture actually of the black hole at the center of our galaxy, not made from a star, but I'll just show you a black hole anyways, now that we have a couple of photographs of them. This black hole is about 4 million times the mass of the sun at the center of our galaxy. And so that's what a black hole would look like. And it's kind of weird how you're seeing this, because you're actually seeing the front and the back at the same time, the way the light works, because it's stronger than light. Yep.
The reason why this happens is because black holes have a singularity that has an infinitely small point of infinite gravity. That way it warps time and space.
Well, I like this. That's right. Yeah. Yep. Yeah. The gravity's so strong that light can't escape it. It's you have to go faster than light, and probably much faster than light to escape a black hole. And I think we have another one here.
It's possible because they delete information.
They what?
They delete information. Say an asteroid falls into it, it is gone. There is no trace of it left.
Possibly.
Not even a fragment of an atom.
Not according to Hawking's radiation. Because Hawking's radiation says that
Some chunk escapes.
that when you have when particles are created, it doesn't matter what particle it is. There's always the particle and the antiparticle. And if you have these virtual particles that in space, like space is, we think of space as empty, but it's actually bubbling with these virtual particles that in the size of the nucleus of an atom, trillions of times every second, these virtual particles are popping in and popping out of existence. Basically, you have the particle and the antiparticle, and then they annihilate each other. But they think that these particles in space that are created near the event horizon, and the event horizon is just, say you have the black hole here, the star's collapsed. Well, there's an area around it where the gravity is so strong that if you cross that line, the event horizon they call it, you'll be sucked into the black hole. You can't escape. And so you have these virtual particles that are formed right near the event horizon. One of the particles will fall in while the other one shoots out. And the one that shoots out actually gains energy from the rotational mass of the black hole, so it actually takes mass away from the black hole. And over time, the black holes will evaporate because of the Hawking's radiation. Because the particle that's, you have one particle that falls into the black hole, the other one does not fall in, it shoots out into the universe, and it gains energy from the black hole to escape it. And by that, it's the black hole is actually shrinking. Yep.
Something vaguely similar to this happened once. A black hole once shot out a spaghettified star. I forget which black hole this was, but it did.
Black hole shot out a star?
Well, it just suddenly reverse deleted a spaghettified star that it probably destroyed way before we even existed.
Yeah. But I'm kind of lost there. You're saying the star?
The spaghettified star, which was a cloud of plasma at that point,
Yep.
was shot out of a black hole. It just happened. We don't know how. It could be quantum tunneling. We have no clue.
Unless it hit the poles of the black hole. Because the black hole's rotating, and sometimes some of the matter gets to the poles, and that can cause these jets to shoot out. Maybe that's what you're talking about? No?
I'll explain it later. I'll explain
All right.
afterwards.
All right. And then some other stars, if they're over 50 times the mass, sometimes they just go into a black hole without any supernova. And that's the case of this star here. Back in, I forget what year that was. It says right up top. So it's 2007, they saw this star. In 2015, they went back, and the star is gone. And the star was over 50 times the mass of the sun, and basically the whole star just collapsed into a black hole. No supernova or anything, just collapsed. And sometimes that can happen with stars over 50 times the mass of the sun. Oh, wrong way again. Yeah, wrong way again. And I'll just show you this black hole here. This is the largest black hole we've found so far. This is in the galaxy M87. And this black hole has a mass of 6.5 billion of our stars. You see how the event horizon here, you see how large it is. This is our solar system right there inside this. So it's a massive one. But again, these are inside the center of galaxies and not formed by stars itself. But I just want to show you that because it's a pretty cool picture. And then we bring back to our Earth. And smile because everybody's in that picture somewhere. Yeah. Hope you're smiling that day. Yep. And basically our little round ball is 7,900 miles in diameter, and our little spaceship in the sky that has everything that we need as long as we don't destroy it. And then, this is one of my paintings of our place in the galaxy. And so I just want to show you that.
How'd you paint that?
What's that?
Oil, or what did you paint?
Acrylic.
Acrylic.
Yeah.
It's stunning. That's all I have to say.
Yeah. Like every star is right where it belongs, and pretty tedious paintings, but they're pretty cool when they're finished.
There's the Earth. What is that the moon?
Yeah.
Or
The Earth and the moon.
all right, you're showing the moon from a closer perspective.
From the opposite side, yeah.
Yeah.
I'm sorry, you actually studied star positions for this painting.
Yep. Yep.
You deserve a blue ribbon.
Yeah, that sounds tedious.
Yeah, it's very tedious. Yeah, this painting took me a year and a half.
But you know what?
What?
You wouldn't know.
Actually, I had this at the gallery, the church on 102, Phil Prima's gallery, and he had an astronomer, and he told astronomers the artist says this is every star is right where it belongs. The artist looked at it. He's like, yeah, he's right. They're So I'm happy I did that for that one person.
I see one of the dippers in there.
Yeah, you got the Little Dipper. Where's that up here? Yeah, right here. Then I had to bring the Big Dipper down here. It would have been off the page. I know. So I guess that's our talk here. Any questions or? Yep. Yeah, you can turn the light on. Thanks.
Yeah, this is going way back to sort of before talking about the size of the universe
Yep.
and the observable universe. And there were three numbers throughout 13.8 million years, billion years ago, right?
Yep.
Was the Big Bang. 13.4 billion is as far as we've ever seen a star.
Yep.
And you said
Or galaxies. We're not seeing stars. We're seeing galaxies. Yep.
Okay.
Yeah.
And you think the entire universe might be up to 17 times.
Probably it's the smallest is
At least.
at least it could be
So
a lot.
I'm trying to think why it would be that much bigger if 13.4 is that because the universe is expanding all this time?
When the Big Bang happened, expansion of the universe, it was faster than the only thing that would go faster than light is space. Space was basically expanding a lot faster than light.
So that
They're saying
that's why it's so much bigger than it would have been at the time of the Big Bang.
It would have only taken a couple seconds for the universe to go from that small to the visible universe.
And has it been expanding at a decreasing rate or an increasing rate?
We figured it was going to be decreasing because logic will tell you that.
Right.
But in the 90s, they looked at the farthest galaxies, and they're like, the universe is expanding faster. And they have no idea why. And they contribute to dark energy Dark just means we don't know. Same thing with dark matter. We don't know what that is either. But something about 8 billion years ago caused the universe was actually slowing down. Then 8 billion years ago, dark energy became stronger than gravity of the universe, and the universe has been speeding up ever since. And so, say if we're here, and we look at a galaxy 3.26 light years away from us, a million light years away from us, that galaxy is moving away from us at 42 miles an hour. Now, if we take another galaxy twice that distance, to this galaxy, it's moving 42 miles an hour. For us, it's moving twice as fast, 84. And if you take a galaxy 3 times faster, that's moving 3 times faster. You go 100 times, a galaxy 100 times further away, it's moving 100 times faster. And so by the time you get to the edge of the galaxies, it appears those galaxies are moving faster than the speed of light away from us. We're moving just as fast as they are, but space is expanding. Yep.
So, on that, would you speak a little bit about the difference in one technique of measuring versus, I believe it's called the Hubble constant, the radiation background radiation?
Yep.
And there's a difference.
There's
really substantial.
Yeah, they're not sure what's going on because looking at the galaxies expanding, they come up with like 42 miles per second. I might have said that per hour, per second. The galaxies are moving away from us. This other measurement, it's a little bit less than that.
Yeah.
And so they're not sure what's going on, but they took the Hubble, they are coming out with different answers with the Hubble telescope and the James Webb. So they took both telescopes, looked at the same object, and it appears that different places of the universe are expanding at different speeds. And so they're not sure why. And so that came out maybe a little less than a year ago. So they're trying to figure out why, if it's right, if their calculations are right, but it appears that the universe may be expanding at different places, different speeds.
So what?
And they don't know.
It gets complicated.
Yeah, yep.
Do all these professional astronomers, or whatever you want to call them, well-known astronomers, all agree that the Big Bang is really the concept? I mean, it is hard to believe that all this came from this little point of matter or whatever, energy smaller than an atom.
Yep.
It's all these giant.
Yep. Well, what they do is they look at all the galaxies moving away from us, and they play it in reverse. And when they do, 13 billion, they all come together. So it doesn't matter where everything came together at a single point. Yep.
So what's helium-3? That's some energy source that's on the moon, or
you could have helium-3, helium-4, helium-7. There's different isotopes. And as long as helium always has 2 protons, the number of neutrons can vary. Some are stable, some are unstable. Yeah. So the element is determined by the number of protons, and then the neutrons can vary. They don't have to be equal. It's more stable if they're equal with the protons.
Okay.
But sometimes not.
When they say that everything was, back Big Bang, when it was just that tiny speck, there was no space out there. It's not like a speck sitting in space.
No,
there was no space.
There was, time and space were all in there. Yep. And then, yep.
I'm going to stop you there, and then if anybody wants to stay and ask you a few more questions, is that all right?
Sure.
All right. Well, thank you again for Rick.
Nice to come, everybody. Thank you.